Okay? So let's see. So what is enthalpy? Okay? So I'll remind you that in the first law of thermodynamics, okay, delta E is Q plus W. Okay? Well, what happens when there's no change in pressure? Or no change in volume. So we'll say no change in PV. Okay? Then is there any work done? Nope. So work goes to 0. Okay? So if there's no change in pressure or volume, then we call that little subscript P right there, that denotes constant pressure. Okay? And now specifically this heat that we're delivering at constant pressure, we define as enthalpy. Okay? So as you can tell, it's going to have the same units as all of the other stuff, joules and or kilojoules. Okay? But specifically, enthalpy is the heat absorbed by an endothermic process or given off by an exothermic process occurring at constant pressure. So these can be chemical or physical changes. All right? And so when we talk about enthalpy in chemistry, it's kind of a blanket or like an umbrella term for a lot of different things. Okay? So it's the heat accompanied with physical or chemical changes occurring at constant pressure. And so why constant pressure? What's the big deal about that? Well, if you think about how we do things in a laboratory, right, where we're mixing beakers and stuff, the pressure is constant, right? We're not doing things in a balloon. We're not doing things up at the International Space Station. We're not doing things at the bottom of the ocean where we're like moving up and down and changing pressure rapidly. We do 99% of our chemistry at a lab bench where pressure is constant. Okay? So we have this term called enthalpy, which is just a blanket term for heat. It's just a type of heat. But specifically, okay, capital letter, it's a state function. So with respect to enthalpy, we only care about the final state and the initial state. You guessed it. Okay? So here's some examples. Okay? So we talked about phase changes earlier and how there's going to be heat either leaving a phase or having to go into a phase. So for example, to melt ice, as it turns out, it takes positive 6.01 kilojoules for every mole of ice to melt. Okay? So this delta H fuse, we put that little subscript fuse for fusion, or I could write this as the delta H of melting, for example. We also have delta H of vaporization, delta H vape. I could also call that delta H of boiling if I wanted. So that gives me the actual quantity of energy I need to boil an amount of water. So I need positive, right, because the heat has to go into the water to melt it, or to boil it, for this example. 40.67 kilojoules for every mole, right? So if, let's say, I want to melt, or excuse me, let's say I want to boil 2 moles of water. Suppose I want to boil 2 moles of water. Then I'm going to multiply this by 2 moles, and let's say 40.67 times 2, meaning I would have to supply my 2 moles of water with 81.34 kilojoules of heat. Okay? So that's what's useful about these delta H's. They allow us to calculate or predict how much energy we need to do something. So what's also pretty cool about this, and again, this is less intuitive, I think, but so if it takes 40.67 kilojoules to boil water, if I were to now condense water, I get the same quantity of heat back out into the surroundings, which you don't really think about, but it's true. When you condense some water, there's a huge amount of heat that gets released. We often call this the latent heat. Latent, am I spelling this correctly? I'm a terrible speller. Latent, oh my God, now I'm having a brain fade moment. Latent heat of evaporation or condensation, okay? So this is happening in the atmosphere all the time when you think about weather systems occurring on big, massive scales, all of this water condensing in the form of rain, and it releases a ton of heat back out into the atmosphere, okay? Or similarly, when all of that liquid water fuses into a solid or freezes, okay? There's a lot of release of heat, that negative sign, okay? So we want to use these quantities, these energy quantities per mole in the same way we've used every other quantity in this class via the process of dimensional analysis, okay? So here's some other examples of chemical changes in enthalpy. So this is the same slide I showed you before, but now, based on this, there is a release of heat, and specifically for this reaction, the delta H, and I'll write delta H, and I like to write RXN for reaction. Okay, for this reaction, it's negative 242 kilojoules for every mole combusted. All right, so this is global for the reaction, but let's suppose we look at this for the 2 moles of water created, right? How much energy will be released? Well, in the same way I did that other calculation, right? If I make 2 moles of water from this reaction, the energy released will actually be 2 times this number, okay? Because this number is the amount of energy released per mole of reactant or product, right? But now for the way that the reaction is written, if 2 moles of H2O are created, then I'm going to have, what is that, negative 484 kilojoules of total energy released. So again, pay attention to that per mole quantity. So what if I had 18.562 grams of water created in this reaction? Well, then we would go through and do our stoichiometry, and I'm going to give you an example of that soon, okay? So here are all of our various flavors of enthalpy. So I'll remind you, that's what we talked about in the learning goals. Know what enthalpy is in all of its various forms, okay? So here's 4 examples that I'm going to give you. There's the standard enthalpy of formation, the heat of formation, ΔHf. This little 0 right here, that means standard. And that standard means it's occurring at room temperature, okay? So that is the heat that would be released for this reaction at 298 K. So when we see that little superscript 0, that means standard. That little F in this case, for this flavor, means formation. And what is the enthalpy of formation? Well, it's the change in enthalpy that accompanies the formation of 1 mole of a compound from all of its elements with all their substances in their standard state. What does standard state mean? I'm going to review this again, but standard state means what phase is that substance at 298 Kelvin, okay? So for example, this, as it turns out, this reaction is the standard enthalpy of formation of H2O. And really, we'd have to write it as H2 gas, that's the standard state, plus 1/2 O2 gas. Oxygen is a gas at room temperature, and this would make 1 single mole of H2O, okay? So this would give me the delta H of formation of water, and that's 242 kilojoules per mole. With 1 mole, it'd take 242 kilojoules to form water from its elements at standard state. Okay, so that's what delta HF means. Well, delta H reaction, this next one, and again, I often like to write that as RXN as an abbreviation, with the little standard, of course, if that's occurring at 298. So that's very similar to this heat of formation, but now that's the change in enthalpy that accompanies any chemical reaction. So it doesn't have to be the chemical reaction written in a standard state from its standard elements. So for example, this just so happens to be a chemical reaction, right? So I could say delta HF or delta HRXN for this particular reaction, because again, this is a reaction that's forming water from its elements at standard state. However, I can also use this delta H reaction for any old generic reaction that we might encounter in this class. Doesn't have to be a reaction forming the compound from its elements in their standard states. All right. So, and then we talked about these two, delta H of vape and delta H of fusion. So this delta H of vape is the standard enthalpy of vaporization, or the heat of vaporization. So the change in enthalpy that accompanies evaporating 1 mole of liquid. Or delta H of fusion, the change in enthalpy that accompanies melting 1 mole of a solid. And again, because these quantities are per mole, right, they're all some kilojoule per mole, okay, I recognize that I can do this process of stoichiometry with this quantity, right, depending on what I'm given in a problem, okay? So suppose I'm given grams or milliliters or whatever, right? So I can use that in my dimensional analysis to do these types of calculations, okay? So let's do a sample problem.